So the first model that we're going to look at, the Bohr model. What kind of a sign is that? Type of sign? It's a neon sign, right? Neon signs actually have neon gas in them. This orange color here is from neon gas. The blue is from a different gas, but the orange is from neon. And the way a neon light works is we've got the neon gas in this tube, and it's somewhat like a fluorescent light. You pass electricity through the gas, and it glows. So the atoms absorb electrical energy, and then they re-emit that as light, visible light. The light emitted by different elements is different in color. So this is a picture of a mercury lamp, and it looks blue. It gives off blue light. This is a hydrogen lamp, and it gives off kind of a pinkish light. What did we learn about the differences in the colors of light? It reflects different wavelengths, right? And the wavelength is related to the energy. When we take light from, say, a hydrogen lamp and pass it through a slit and through a prism, like we did with the light from the incandescent light bulb or from the sun, what we see is not a continuous rainbow, but we see individual lines of color with blackness in between. This is not real visible on the screen here. There's a blue line. Oh, that's purple. Purple and blue and red up here. So instead of seeing the whole rainbow, we just see a couple of lines. This light is separated into its wavelengths just like the light from the sun is, but it doesn't have all the colors in it. It only has a couple. So this is what we get from white light. And we say this is a continuous spectrum. It's got some radiation at every wavelength. From a hydrogen light, we get 3 lines. So the light coming out of hydrogen only has certain energies, has certain wavelengths. Here's helium, it's got a few more lines. Neon has a lot of lines, but it's still not continuous. Neon is a larger atom than helium. Helium is larger than hydrogen. It seems that the larger the atom, the more lines there are. So these are called emission spectra. So the emission spectra of an individual element has light of only certain wavelengths. And they observed this. This was observed, and they tried to figure out why. Why does it do that? They didn't expect it to do that. What's going on? Well, Bohr came up with a model that explained the emission spectrum of hydrogen. And it really nailed hydrogen. It was really awesome. The biggest problem with it is it only worked for hydrogen, right? So that just doesn't make it very useful. So why do we still teach it to you? Because it's easier to understand. And it was an important step in developing future understanding. So why do those excited atoms only emit light at particular wavelengths? Well, this is the Bohr model. This is an illustration. It's a little bit like the solar system. Here we have the nucleus in the middle, and the nucleus has all the protons and neutrons in it. And then the electrons are going around in orbits, just like the planets orbit the sun. Okay, the Earth has a fixed orbit around the sun. It doesn't move around randomly. We can predict where it's going to go and where it's going to be, and we can predict all those things. That's what astronomy does. And so this is a nice model. It's kind of comforting because we understand it, and we think of the electrons going around in circles, and this is very nice. So the idea here is that these different orbits have different amounts of energy. And the light, I should see what's coming up next. Yeah, this is probably a better place to explain that. So we can think of those different orbits as being like rungs on a ladder. They're quantized. When you're climbing a ladder, this is kind of a funky ladder, right, because it's not evenly spaced. When you're climbing a ladder, you can put your feet and stand on the first rung, or you can stand on the second rung. Can you stand between? No, you can't. You could try, but you're going to fall down to the first rung. So there are only particular levels that you can be at. That's what it means to be quantized. We have a lot of examples of quantized things in everyday life. A set of stairs is quantized. You can be on the first step or the second step. That's different from a ramp, where you could just edge up a little bit at a time. The grades in school, you're in first grade or you're in second grade. You can't be in 3.5 grade, right? One or the other. Our monetary system is quantized. There are pennies and nickels and dimes and quarters and 50-cent pieces and dollar bills. There's no 7.5-cent coin. It's quantized. So those orbits in the Bohr model are specified by quantum numbers. And that's given the symbol n, and they're just 1, 2, 3. The first one, the second one, the third one, the fourth one, etc. from the nucleus. And it's impossible for an electron to exist between orbits. It has to be in orbit 1 or in orbit 2. And those orbits have different amounts of energy. Just like these have different distances above the ground. And the higher you go, the higher your potential energy, and the more it's going to hurt if you fall off the ladder, right? Well, what happens when an atom absorbs energy, like in one of those hydrogen lamps? What happens is, as the energy comes in to this electron, remember, hydrogen only has one electron, right? That electron's going to hang out in the first lowest energy level most of the time. But here comes energy in, and the electron can absorb it and jump up to a higher level. It's not stable up there. We say that's an excited state. It's not stable. It'll be up there for a little bit, and then it will relax. It'll come down. It can come down to the next level, or it can come all the way down to the ground level. And just like when you're climbing a ladder, you don't actually have to step on each rung, or if you're doing the stairs, you can take stairs 2 or 3 at a time, right? You don't have to go one at a time. So this electron can skip over the second level and go directly to the third. But eventually it's going to come down. When it comes down, the energy that it took in has to go somewhere. And it's going to be given back out, and it's going to come out as light. The light we see as different colors depending on the energy of the light, the wavelength of the light. And so the different colors that are emitted tell us that these electrons are making different transitions within these orbits. So when the electron relaxes from its excited state back to a lower state, it emits a photon, or a quantum of light. Seriously? The light emitted by these excited atoms gives us these specific lines at specific wavelengths. So this 657 nanometer red line that we see comes from an electron moving from the third level to the second level. This blue-green one has a wavelength of 486 nanometers, and that's a transition from the fourth to the second. And this violet light is from the fifth to the second light orbit of hydrogen. Because we can measure these wavelengths and their energies, we can calculate the energies of the electrons in the atom. It's really cool. So it was awesome. It predicted the lines of the hydrogen emission spectrum. Problem is, it failed to predict the emission spectra of other elements that contained more than one electron. So really limited use. The Bohr model was then replaced with a more sophisticated model called the quantum mechanical model. And this is what those famous scientists were saying they didn't like.